Hello everyone, at last we are on to the SMO Open mock paper. As I mentioned in the intro video, this is a pretty difficult mock paper in the sense that although the SMO Open is already quite difficult to complete, you may find that you don't even have enough space to think about each of these 25 questions in a 2.5 hour time frame. So if you had tried to do the mock paper as a 2.5 hour paper and felt that you ran out of time, feel free to look at these problems again before watching the rest of the video. We'll be only going through questions 1 to 5 here, but the same thing applies for all the others as well. In most of the SMO Opens, the front half is supposed to be more approachable. Approachable doesn't mean easy, but approachable means a bit closer to the sort of things that regular A-level students would be familiar with, except with a lot less help than would be the case in the A-levels. So these are the sort of problems where, given sufficient time, you would hopefully be able to deduce the correct approach. Now, let's start off with question 1. We are asked to simply evaluate this sum, and the sum involves some products, including a power of 2 at the top. However, we don't really want to start with the power of 2 at the top. Now, remember that whenever you're asked to add up a bunch of terms like these, it should likely be that you can either pair things up or that you would be able to get a telescoping sum, i.e. using a method of differences. Now, if you don't see any plausible way in which you can pair things up here, then method of differences is the way to go. And if you want to know how am I going to make a difference show up, then logically, partial fractions is what you kind of can see here. So we can ignore the parts with the power of 2 first and just look at the rest of the fraction. And the rest of the fraction is in the form n over n plus 1, n plus 2. So the fractions are of this form, and you hope that it would turn out to be a difference. Thankfully, it is equal to a difference. I'm not going to go into the details of the partial fraction decomposition. I hope you are able to do that on your own. Now, this is something that for the SMO Open is quite inevitable. We won't be able to go through every single detail of the technical steps. We just want to go through the main ideas. Otherwise, this video is going to take way too long, and the later videos are definitely going to take way too long. So this is going to be your telescoping sum. And if you multiply by 2 to the power of n, you will see why it's a telescoping sum. The first term at the top becomes 2 to the n plus 1. Sorry. 2 to the n plus 1 over n plus 2, while the other is 2 to the power of n over n plus 1. And you see that these are the same kind of terms except with the n moving forward by 1 step. So that is precisely what we hope to accomplish in the method of differences. So if you sum from n equals to 1 all the way to n equals to 14, you would expect that everything would cancel off except the first and the last term. So the largest one would be when you put n equals to 14 here, and you get 2 to the power of 15 over 16. The smallest will be when you put n equals to 1 into here, and it's just 2 over 2. Okay, so this would be 2 to the power of 11 minus 1, and that is equal to 2047. Second question is a trigonometric one. You're given alpha and beta angles in the first quadrant. You are told cosine alpha plus beta and sine alpha minus beta, and are asked to find tangent alpha over tangent beta. I think it's fairly obvious that this has not much to do with tangents really. Since we have sines and cosines, we shall start off by just using tangent as sine over cosine and rewrite the expression in terms of nothing more than sine and cosine. So it's sine over cosine at the top, sine over cosine at the bottom. And we can rearrange this to be sine alpha cos beta. It really looks promising, doesn't it? Over cosine alpha sine beta. What we get here is something that looks very much like our product to sum, and it is pretty much assured that it is really product to sum by the two things that they give us, which is using cosine alpha plus beta and sine alpha minus beta. So how we would do the top would be sine alpha plus beta plus sine alpha minus beta. And the bottom is the same except with minus sine alpha minus beta. Now normally there would be a 2 here, but because it's at the top and bottom, we can just ignore the factor of 2 that should be there. The question, of course, is not giving us sine and sine, it's giving us a sine and a cosine, but that's not much of a problem. It's not much of a problem because the ratio is simply in our 3, 4, 5 triangle. If cosine is 3/5, then sine would be 4/5. Right? We don't have to worry about negatives because alpha and beta are in the first quadrant. So alpha plus beta is going to be either in the first or second quadrant, which is still going to be positive in either case. Okay, great. So we just need to substitute in, and this is nothing more than a standard computation. Okay, so the fraction should be 19 over 9, and your answer would be 28. Now for trigo questions, you might say, how am I supposed to know that I should do this? And the answer is, occasionally you will take a wrong turn. And if it just looks like it's getting worse and worse, then just abort and try something totally different. Okay. Question 3 is an algebraic problem. X, Y, Z are positive reals that satisfy these two equations. Determine the value of x plus y plus z. Now, note that visually we can already tell this is a very symmetric looking pair of equations. By symmetric, what we mean is that if you just swap around x, y, z in any way you like, you still get the same thing. And so our treatment of it should also be as symmetric as possible. We don't want to, let's say, substitute in x equals to something in terms of y and z, and then after that mess up the whole equation. We want something nicer than that. Usually it will turn out to be nice. Now, probably the easiest way to bring out the symmetry is to clear out all the fractions. So multiply everything by x, y, z, both the first and the second one. The first one, if multiplied by x, y, z, gives you xy plus xz plus yz. Not in the same order, but it doesn't matter. This symmetric sum is equal to 6xyz. The second equation, if you multiply xyz, you would get 2022x, 2022y, and 2022z, which I'll write it down that way. And then you would have minus 6x squared minus 6y squared minus 6z squared. and this is equal to 72 xyz. Now you can see here that from the question, you are supposed to find x plus y plus z, which shows up in the second equation. You also get some sense that x squared plus y squared plus z squared and xy, xz, and yz could maybe be x plus y plus z squared. But xyz is fairly useless here. So it makes sense to just substitute it away and write this as 12 xy plus xz plus yz. Now, upon doing this, hopefully you would realize that the x squared plus y squared plus z squared and xy plus xz and plus yz are exactly in the correct ratio of 1:2, meaning that if we move it to the other side, 2022 x plus y plus z would just be equal to 6 times of x plus y plus z squared. Normally, I would suggest a substitution, but I think this is one case where we really don't need to substitute anything. They are positive, so x plus y plus z is non-zero, so we can just cancel off one factor of x plus y plus z and divide over by 6. So x plus y plus z is 2022 over 6. And there we go. Another question that we'll try to make use of symmetry for in an algebraic sense is question 4. Straight away, you know that if you try squaring this whole thing, you're going to regret it a lot because these are going to be quite horrible. At the same time, we're asked to find a solution to this equation. So we still have to solve it. It is not a case where, like the previous problem, we are asked to find something like x plus y plus z. We're asked to actually find x. So we have to solve it in some way. Nonetheless, if we pay attention, we notice that x plus 20, x plus 22 actually multiply 2x squared plus 42x plus 440. So it stands to reason that that's what's going on here, right? The two expressions here are related to the other square root. The right side, maybe not so much yet. But what we can do is just to do a substitution. Substitution would be to let maybe P and Q be root x plus 20 and root x plus 22. So that the left side would be 2pq minus p minus q. Now, a key decision is what we do on the right side. How do we substitute for the 8 minus 2x? And the answer is that we want to keep it symmetric as far as possible. So, in view of that, I can say that x is equal to p squared minus 20. I can also say that x is equal to q squared minus 22. And so I'll just do both of them, right? I'll use 2x as this x plus that x. Remember that by making it symmetric, it gives us the best chance of having a nice factorization. Okay, so shift everything over. And you would get p squared plus q squared plus 2p cubed. Precisely what we were hoping for. So p plus q squared minus p minus q can be written as minus p plus q. And the rest of it is just going to be 90. This is a simple enough quadratic in terms of p and q. We note that it must be positive because they are both square roots. So the sum is also going to be positive. So I can just say that here p plus q would be 9. So it would be 10 and not minus 9. Now to solve this equation is also not very difficult because if p equals to this and q equals to this, the relationship between them is simply that q squared minus p squared equals to 2. So we can solve it. Since p plus q is 10, we divide it off. Q minus p would be 2 over 10, which is 1/5. I'll write it as a decimal, 0.2. And just combine these two equations to get q equals to 5.1. So your solution, A, would be 5.1 squared minus 22. Which is 4.01. And 4.01, the answer extraction is to write it as a fraction and add the numerator and denominator. So it's simply 401 over 100 and answer is 501. Yeah, of course, it would be not much difference if you just solve the equation as root x plus 20 plus root x plus 22 equals to 10 and square both sides and solve it like a normal third equation. That would have worked perfectly fine too, as long as you didn't try to square it at the very start. That would not have gone very well. Finally, we are at question 5. Question 5 asks you for the smallest positive value of x in degrees for which this function fx equals to sine x over 20 plus cosine x over 22 attains its minimum value. Identities don't seem to work very well here, right? Because x over 20 and x over 22 are in a very awkward 10:11 ratio. So if you try to do, let's say, a sum to product after changing cosine to sine 90 degrees minus x over 22, you would get quite a horrible mess. Instead, we're going to do something that is a lot simpler and yet somehow a bit less obvious. We're just going to ask ourselves, what would be the theoretical minimum? How small could it really go at the absolute minimum? What could it be? Well, even though we don't know whether it could really happen, we know that the theoretical minimum is if sine can be -1 and cosine could also be -1 at the same time, and then x would be -2, if that could happen. Can it happen? Well, potentially yes. It can happen, and it will happen, if x over 20 and x over 22 both appear at the correct position. We know that sine would be -1 at 270 degrees. And we know that cosine is -1 at 180 degrees. Okay, I'll use a different variable. I'll use n and m. So we want to make sure that we can find such an x that would make both m and n integers. Well, positive integers, but that's a granted if x is positive. So obviously the reasonable thing to do would be to just write x in terms of n, x in terms of m, and equate them. It looks like the numbers are pretty large, but it also is quite clear that everything's a multiple of 90. So after equating them, lots of stuff are going to cancel off anyway. Okay, so equate them. And we would get 1440 is equal to 7920 m minus 7200. We can divide by 720. So 2 equals to 11m minus 10n. And thankfully, this is actually really clear, right? The smallest value in which this occurs would simply be m equals to n equals to 2. So substitute that in, and you will get x is equal to a remarkably large 19,600 in degrees. So this again goes back to what we mentioned about Trigo a moment ago. How do we know this is the correct approach? We may not have known this, but if you were trying to use identities for a while and you realize that they're just making things worse and worse, then just abort identities and look at the equation again. Is there something else that we can do? Who knows if there is something totally unrelated like AMGM, or it could be the R formula, something ridiculous. But for the most part, it would be clear that none of those work, and therefore we go back to first principles, which is how small can sine and cosine be. Alright, so that's all for this video. We'll be going through the rest of the problems in subsequent videos, so do look out for that. Thanks for watching and see you then.